Welcome back, everyone. I'm Jordan Giesige, and this is The Limiting Factor. Today we're going to be reviewing the progress and timeline of Tesla's 4680 battery cell factory at Giga Berlin. This video won't cover Cato Road in Fremont, California, but there will be a quick note on Giga Austin at the end. When we have more information on Cato Road and Giga Austin, I'll make another video, hopefully after Tesla's Q2 earnings call. Before we begin, a special thanks to my Patreon supporters and YouTube members. This is the support that gives me the freedom to avoid chasing the algorithm and sponsors, and I hope will eventually allow me to do this full time. As always, the links for support are in the description. Giga Berlin's construction application has recently been made public, which has resulted in an explosion of updates for Tesla's cell production plans in Germany. Tobias Lind has done a great job of digging through the documentation, and I recommend supporting him on Patreon if you can. I regularly use Toby's drone footage of construction at Giga Berlin at the end of my videos, and the footage and insights he provides to the Tesla community are super helpful. Let's start with this image of Tesla's property, which lists all of the buildings on Tesla's Berlin property and the manufacturing processes they house. We're going to focus on just the battery-related buildings, so we'll eliminate the names for the other buildings and then zoom in from there. CP stands for cell production and BP stands for battery pack production. Battery pack production shares a building with DU, which is drive unit production. The reason why battery pack and drive unit production are housed in the same building will be made clear later in the video. Let's align what we see here with a screenshot taken from drone footage from Tobias. As you can see in this photo, which was taken several weeks ago, the foundations are mostly poured for the cell production building, and the building for battery pack production is complete. If we return to the map, it shows that the building for battery pack production is roughly the same area as the cell production building. It took about 3 months for the external structure of the battery pack building to be completed. The implication here is that if the foundations are mostly poured for the cell production building, the external structure should be completed by September. Let's look at a few points of interest in and around the cell production building. In the next slide, we're going to look at a cross-section of the cell production building. I've marked in red where the slice for the cross-section is taken from. As you can see here, the cell production building will be 4 stories tall, and it looks to be about the same height as the other buildings at the Giga Berlin site. In the part of the factory shown by this cross-section, cathode and anode production appeared to be in a 2-story high production hall with catwalks. This makes sense because, as Tesla showed at Battery Day, the mixing and coating equipment for the cathode and anode production is about 2 to 3 times taller than the average person. If we look back at the image from Tobias, foundation work is still occurring in the area where cathode and anode production will be. Adjacent to the cathode and anode production area is a pit where the foundations appear complete. Let's take a look at the schematic of the first floor to work out what that pit might be for. I've marked in pink the area that aligns with the pit that we saw in the last image. If we zoom into that part of the schematic, we can see that it's for can stamping. The cell cans are the outside shell of the battery cell, and my understanding is that Tesla has been making cell cans for years for the 2170 cells at Giga Nevada. Regardless, stamping and forming metal is something Tesla has a lot of experience with, so this part of the factory should come together quickly. We won't look at the second and fourth floor because this is an update video rather than a top-to-bottom walkthrough of cell manufacturing. I've done walkthrough videos of battery cell manufacturing in several videos, including the battery factory video. In terms of the overall cell production process, everything I'm seeing in the factory is what I've laid out in past videos. However, the third floor does have a point of interest. If we zoom in one level, we begin to see what looks like manufacturing stations, but it's still difficult to make out what's going on here. Let's zoom in even further to one manufacturing station. This is the tabless production area, and we can see 4 workers at this station alone. I could be incorrect, and these figures could be something else, but it sure looks like workstations with workers to me. If we zoom back out, that's 64 workers for just this part of the factory, meaning Tesla's battery cell factory is fairly labor-intensive. I was hoping we might see full automation in the entire process, but I'm not disappointed. It makes it clear to me that this is version 1 of Tesla's full-scale battery cell factory, and there's further room for improvement in the future. Let's move on to another document from Tobias Lind. Several people asked me to comment on this section of the wording, which has been translated from German to English thanks to Scott Otis. This lays out the process I've described in the past, but there are two pieces of information that caught my eye. First, the current collector foils for the cathode and anode electrodes are pre-coated with adhesive before being coated with active materials. I hadn't heard of foils being pre-coated before, but Battery Bulletin, who has in-depth understanding of the battery industry, advised that it's common to coat the current collector foils with carbon for better adhesion and corrosion resistance. Whether Tesla is using something else, I don't know, but I'll keep my eye out for information. The second thing that caught my eye is that the aging time is roughly 10 days. My past research indicated aging could take around 3 weeks, but I didn't know if that was correct because information in research papers doesn't always align to the realities of battery manufacturing. As a reminder, aging occurs after a battery cell is charged for the first time in a factory. During the aging process, the battery cell is, for a lack of a better term, ripened. Meanwhile, it's monitored and quality checked for any defects that arise. On this point, Battery Bulletin advised that a few companies are now doing aging in 10 to 15 days. So even as a new battery manufacturer, Tesla appears to be at the leading edge. The shorter the aging time, the better, because it reduces storage costs and increases cash flow by getting the batteries into the hands of customers sooner. The next slide is a flow sheet with most of the wording blacked out. Again, this aligns with the process I've described in past videos. I'm showing that process again here with an outline of the steps covered in the flow sheet. There is one variation between my flow sheet and Tesla's, which is that Tesla's indicates the point at which the tabless process occurs, whereas mine didn't. In the center of Tesla's flow sheet, I've marked the tabless process in pink. If you'd like to know more about what a tabless cell is, check out my video on the tabless electrode. Many people have called the phrase tabless electrode a misnomer because it's actually hundreds of tabs forming a contiguous array. However, tabless is easier to say, so that's the word I'll use. The flowsheet doesn't specify what's meant by tabless process, but I'm assuming it means cutting and possibly folding the tabs. It makes sense for the tabs to be cut here because the previous step was coating the current collector foil with active material to form electrodes, and the next step is assembly, where the jelly roll is inserted into the cell can. The jelly roll is a roll of metal current collectors and active material that are the primary components of a battery cell. I imagine that the cut tabs would be delicate and difficult to handle because the metal current collector of the electrode is as thin as aluminum foil. Cutting the tabs as close to insertion into the cell as possible would eliminate defects caused by handling the delicate tabs. However, cutting the tabs after the cathode material has been applied may cause particle contamination issues. The tabs will be laser cut, and each battery cell will involve hundreds of laser cuts that are probably less than a millimeter away from the active material. If any fumes or particulate from the laser cutting process stuck to the active material, it would become part of the jelly roll. Then, when the battery cell was cycled, it might short out the battery cell by creating an electrical bridge between the positive and negative electrode foils. I'm taking a wild guess here, but this may be what Panasonic was referring to when they said that the 4680 cells are more susceptible to particle contamination and that moving to the 4680 will require them to increase their craftsmanship by 1 or 2 levels. Next up is the timeline for construction and installation activity at Giga Berlin. I've highlighted 2 lines which are for cell and installation BP. Cell is assumed to be for cell production, and I think it's a safe bet that's correct. Installation BP is for the installation of battery pack production equipment because that building is already built. Installation of the equipment for drive unit production, or installation DU, is happening at the same time as battery pack equipment. As you'll recall, drive units and battery packs are housed in the same building. Why is this? My assumption is that it's because the battery pack and drive units are 2 of the primary components that make up the skateboard of Tesla vehicles, so it makes sense for them to be co-located to build the skateboard assembly. As a quick side note, one thing that Tobias was surprised to find was that the body of the vehicle and the skateboard containing the battery pack are separate assemblies that are mated. This is one of the images that he attached to the tweet, and it aligns with what I've stated in past videos. The structural battery pack should be somewhat interchangeable with a conventional battery pack, so long as mounting points are the same. If this doesn't make sense, check out my structural battery pack video if you'd like to know more. The ability to switch to a different pack architecture on the fly would be good news if Tesla has issues with the 4680 cell or pack, and it would allow them to fall back on the conventional 2170 battery cell and pack. The structural battery pack is just as great a concern for me as the 4680 battery cell. This is because both the Model 3 production ramp and the new Plaid Model S production ramp were delayed by issues with pack production and verifying pack safety, respectively. Let's get back to the timeline. The X's indicate when activity is occurring, and the red X's indicate when the maximum amount of noise is expected. As we saw earlier in the video, the building exterior for cell production should be complete by September, but this timeline shows an October completion date. That extra month would allow time for finishing the interior. However, it's unclear whether that would include the installation of manufacturing equipment as well. If it does include manufacturing equipment, it would put Tesla's timeline for the 4680 line ahead of my expectations. If it doesn't include installation, it's right on track with what I predicted, which is that equipment would be installed in Q4 of 2021. Battery pack production equipment and drive unit production equipment will be installed between September and December. This means that if Tesla wants to produce vehicles out of Berlin this year, they may need to ship fully completed skateboards from Fremont to Berlin that contain 4680 cells, a battery pack, and drive units. If the rumors are correct and Berlin plans to start vehicle production in November of 2021, the Giga Berlin factory will only need a few hundred of these fully completed skateboards to start the production ramp. In December, Tesla can stop shipping drive units, and then in January they can stop shipping packs. And if my timeline is correct, then sometime late in the first quarter of 2022, they can stop shipping 4680 cells. Before I wrap things up, a quick note on Giga Austin. There are rumors that this building at Giga Austin is for cell production, which has an exterior that's nearly complete. If that's true, then as suggested in my lithium mine to battery line video, Giga Austin may accelerate past Giga Berlin. However, I'm not convinced of this yet. If Tesla decides to put cell production, pack production, and drive unit production all in the same building, they may want to complete the building early, just as the building for battery pack and drive unit production were completed early in Berlin. Overall, the 4680 production timeline at Giga Austin remains a question mark for me. I haven't seen a set of plans for Giga Austin that are as detailed as we received for Berlin. If you know of such plans, let me know in the comments below. In summary, things are progressing at Berlin roughly in line with the predictions in my lithium mine to battery line video. The key piece of information we're all looking for at the moment is Cato Road, but the fact that cell and pack production facilities are progressing at pace in Berlin indicates that Tesla has a high level of confidence in Cato Road. I'll be looking for advice from Tesla in the upcoming earnings call about the status of Cato Road and their plans for production in Berlin. If there are more details released about Cato Road in the earnings call, I'll do another video to cover that off. If not, the next video will be the second video of the 3-part series on QuantumScape. If you enjoyed this video, please consider supporting me on Patreon with the link at the end of the video. I'm also active on Twitter. You can find the details in the description, and I look forward to hearing from you. A special thanks to Michaelis Studers for your generous support of the channel, my YouTube members, and all the other patrons listed in the credits. I appreciate all your support, and thanks for tuning in.